Bam! Mr. Tarrou. In this math lesson, we're going to do 4 examples where we find complex numbers that satisfy a given equation. And you could argue maybe we're going to do 5 examples because we're going to work out this first example with 2 methods. The second way we work out this problem is actually going to be quicker than our first technique, but there'll be some value into seeing how to solve for this complex number in our equation here with both techniques, because that'll give you options for when you have equations or problems that are more difficult. Okay, and I'm going to put timestamps in the description because there are going to be 5 examples basically, so you can jump ahead if you like. We're going to find the real numbers of a and b, which are basically just our coefficient of our real portion and the coefficient of the imaginary portion of our complex number that satisfy the given equation. Now, if I write this as 4 plus I times z equals 8 minus 3i, I could simply say find the complex number that satisfies this equation. Now, with the way that we're sitting here, we have 4 plus I times a plus b times I equals 8 minus 3i. You may think, hey, we have a couple of binomials. Let's go ahead and multiply those together. So we have 4 times a is 4a. 4 times bi is going to be 4bi, and it's positive. Now we have a positive ai as we distribute these binomials. And then we have 1 times b is b, and I times I is I squared, and that is equal to 8 minus 3i. And this is a somewhat advanced video, so by now I'm sure that you know that I is the square root of -1, therefore I squared is equal to -1. So this I squared is going to become -1, making this basically minus b. So we have 4a minus b plus 4bi plus ai is equal to 8 minus 3i. Now, if you look at the left-hand side of this equation and you decided to distribute these 2 binomials together, then what you want to do is bring together, like I have here, basically your coefficients that are going to be the coefficients of a real value in a sense. Well, I'm misspeaking here a little bit because kind of technically b is a coefficient of our imaginary number or value of I, but I'm grouping together the terms that don't have an I in them, that are in themselves not a coefficient of an imaginary number. And here we have 4b times I plus ai, and I want to match this up and kind of create an equation with the coefficient that I has on the right-hand side of this equation, which is -3. So I want to factor out our common factor of I from these 2 terms. So that's going to give us a plus, and we have 4b plus a, which is a factored coefficient now of I, which is equal to 8 minus 3i. So we have this 4 minus b, which is slightly confusing because in our complex number, b is the coefficient of I. It's the coefficient of our imaginary portion of our complex number, but right here, b doesn't have an I with it. So this is going to be matched up with the 8, and we're going to create a little equation with that and say that we have 4a minus b is equal to 8, setting equal the real parts of the complex number that is on each side of this equation. Now we have a coefficient of I, which is equal to 4b plus a, and we're going to set that up to be equal to the coefficient of I on our right-hand side of our equation. And I'm also going to turn this around because I'm used to seeing the a first, and we have a plus 4b is equal to -3. Okay, so we now just have a linear system, a two variable linear system, comparing the real portion of the complex number on the left to the real portion of the complex number on the right, and the coefficient for I on each side of this equation. And we're just going to solve this little system of equations. And I'm going to do this with linear combination, or you can do substitution. It's perfectly set up for that basically. We have a is equal to -3 minus 4b. I'm going to multiply this first equation by 4 because I'm going to do linear combination. And we have 16a minus 4b is equal to 32. We have a second equation, of course, of 1a plus 4b is equal to negative 3. We have our opposite coefficients here. We're going to add these equations and get 17a is equal to 29, and divide both sides by 17, and we have a is equal to 29 over 17. Well, now that we know what the value of a is, we can plug it into either one of these linear relationships comparing a and b together and solve for b. So we have, let's say that we have here a, which we now know is 29 over 17, plus 4b is equal to negative 3. We're going to subtract both sides by 29 over 17. And you'll see a little bit of an issue here as I make up my own problems to make these videos. We're going to get a little bit nasty here. We're going to multiply this by 17, at least in the sense of trying to do this in my head. So we have 4b is equal to negative 42. Yes, should have just spoke this out as I was doing the problem. 3 times 10 is 30, and 3 times 7 is 21, and 30 and 21 do not make 42. It makes negative 51. So, negative 51 minus 29 is going to give us negative 80. Divide both sides by 4, and we get that b is equal to negative 20 over 17. So that is one way of solving for the real values of a and b, basically our real portion of this complex number, the unknown complex number in our original equation, and b, which is the value, takes on the value of negative 20 over 17. Double check. Perfect. Now, you're going to see plenty of problems, I'm sure, in your textbook and class where you have just terms all over the place on each side of an equation, and you want to compare the real terms and set up an equation from that with the coefficients of your imaginary terms and create a system of equations. But this particular question could have been solved a lot quicker. That example or version is coming up right now. And with our board reset, going back to our original problem, you might do the second technique had I actually asked for the complex number that satisfies this equation and had a z here. But nonetheless, instead of distributing the 4 plus I with the a plus bi, you can just, if this is the variable you're looking for and it's multiplied by a known quantity, you can just divide that away. You might have been watching me do that example and just wondering why I didn't do this in the first place, because the techniques in that previous example may come in handy. And we don't always do questions the most efficient way when we're first learning a concept, or even when we're super comfortable with what we're doing. Yeah, this complex number, a plus bi, is just a quotient of two imaginary or two complex numbers. We don't like to leave I in the denominator of a fraction, kind of like leaving a radical in the denominator. Usually we want to rationalize that denominator and clean it up. We're going to get rid of this I in the denominator, of course, by multiplying the numerator and denominator by the conjugate. And wrap this up in parentheses, and let's go ahead and distribute. We have 8 times 4 is 32. We have 8 times negative I is negative 8i. Now we're looking at negative 12i, and the negative 3 times 4. And negative 3i times negative I is going to be positive 3i squared, which we know I squared is negative 1. And down here we have a difference of squares. This is just going to be 16 minus I squared. Cleaning that up, we have a plus bi is equal to, now this is plus 3i squared, but really it's minus 3. So we have 32 minus 3, which is going to give us that 29 that we had before. And we also have negative 8i minus 12i, which is negative 20i, over 16 minus negative 1. 16 plus 1 is 17. We want to write our complex numbers with a real and an imaginary part, so this is not sort of appropriate to write this. We have a plus bi is equal to 29 over 17 minus 20 over 17i, and here's your value of a, and here's your value of b. So we had two ways of solving or finding the complex number, or the coefficients within that complex number, the real and imaginary coefficients that satisfy this equation. And yeah, one technique was a lot quicker than the other, but here we got the same answer. And really, that's all that matters. Our second example coming up right now. Alrighty then, our second example. We're going to find the complex number z that satisfies this equation, where we have z minus 2i plus 1 over 3 plus 2i is equal to z plus 1 over 1 plus I. And so I'm telling you here that everywhere in the equation that you see a z, we are looking at, that is our complex number. That is our a plus bi. Okay, well, we have an equation where there's one fraction on each side. And how do you go about this? You basically multiply both sides of the equation by 3 plus 2i times I plus, 1 plus I, or you cross multiply. So we're going to go ahead and cross multiply this, and we're going to get z minus 2y. We're not really getting anything, I'm just showing the multiplication. Z minus 2y plus 1 times 1 plus I is equal to z plus 1 times 3 plus 2i. We're going to go ahead and distribute. We have z minus 2i plus 1 times 1, so that's just going to be z minus 2i plus 1. And now we're going to take the term here of I and multiply it to the z, the minus 2i, and the plus 1 to give us plus zi minus 2i squared plus I. And we're going to distribute together these two binomials. We have 3z, and then we've got plus 2zi. Now we've got plus 3 plus 2. That is supposed to be a 1, right? Yeah. Plus 2i. Hate to do this whole example and realize I miscopied my problem. Okay, so what's going on here? Well, we've got just a tiny bit of cleaning up we can do. It seems like we have a big old mess here. We have I squared, which is negative 1, so this is going to become just plus 2. And we've got some like terms here, so we're looking at z. Negative 2i plus I is negative I. We got 1 plus 2, which is 3, plus zi is equal to 3z plus 2zi plus 3 plus 2i. Now here's why I kind of did the first example in two different techniques. We've got basically sort of like real terms. Well, we have terms without i's and terms with i's all over this equation. And we basically want to compare them. So what can we do? We can subtract both sides by 3, which is going to cancel that out. We can subtract both sides by z. We can, we're trying to solve for that complex number. We're trying to solve for z, and you can't solve for a variable when it's on both sides of an equation. So anything that does not have a z, going to the left, minus 2i, minus 2i, and when we move all these terms around, we get negative 1i minus 2i is negative 3i. And just for good measure, maybe show that there is a 0, a real plus an imaginary portion for this complex number. And we've got 3 minus 1 is 2 z, and 2 minus 1 is 1, so we have plus zi. Excellent. Now keep it in mind that we're trying to solve for z. We need to rewrite this right-hand side, do a little factoring so that we only have z showing up once. So we're going to factor out a z, and we have negative 3i is equal to 2 plus I times z, and we're starting to see the end of this come out very, very clearly now. We're going to divide both sides by 2 plus I and get, and I'm going to put this is an equal sign, so I'm going to swap sides so I have some room to work over here. We have z is equal to negative 3i over 2 plus I. So we had a new style of equation. We're asked to basically just solve for z. We're not losing our head. We're kind of pulling on our algebra skills, and we have one fraction equal to one fraction. So we're either multiplying by these all these factors in the denominator to make the divisions cancel away, or just simply doing cross multiplication. Starts to blow up here and look really nasty, but just remember, you're trying to solve for z. Just get that variable together on the same side. Now we have z is equal to negative 3i over 2 plus I. We're going to clean this up one more time by, well, we got more examples coming, but we're going to multiply the numerator and denominator by the conjugate. And we have z is equal to negative 3i times 2 is negative 6i. And then we have negative times negative is positive, so we have a plus 3i squared over, and this is a multiplication of a difference of squares basically pattern, a plus b times a minus b. So we're looking at 4 minus I squared. That means that z is now going to be, with I squared being negative 1, negative 3 minus 6i over 4 minus negative 1. And that's going to give us a final answer of negative 3 over 5. You want to write your complex number with a real portion or term and a negative imaginary term, minus 6 over 5i. And that is the complex value number that satisfies this equation. Example 3 coming up right now. Third example, a little bit of a twist with each one of these new problems we've got. Find the complex number z that satisfies this equation. Okay, remember, this absolute value looking function around our complex number is asking for the modulus of this complex number. And that's going to help us, direct us into the direction that we do this problem, or how we do this problem. Now, because we've got this modulus notation in this equation, it's not something that we're going to just be able to, solve for z. It's kind of hiding the mathematics that you need to tackle to do this problem. So for this particular one, we're going to remember that z is actually representing this complex number, that sort of standard form, if you will, of a plus bi. So here we have plus I times a plus bi. Maybe kind of a little bit weird to see the I times z, but, and you go, well, I already have I in here. No. It's I times that complex number is equal to 5 plus I. Minus I. Now, by bringing in the fact and using the fact that z is equal to a plus bi, actually writing out the two terms of this complex number, then that allows us to recall here that the modulus of z is the square root of a squared plus b squared. Okay, so let's just start doing the algebra. We have an equation with a square root in it. Back in Algebra 2, in earlier classes, if you solved equations with a radical, you would isolate that radical and then apply the inverse math operation. In this case, square both sides of the equation. So we're going to distribute the I. We have the square root of a squared plus b squared is going to be then added to ai plus bi squared equals 5 minus I. Well, let's not forget again that b squared is negative 1. So now we have the square root of a squared plus b squared plus ai minus b is equal to 5 minus I. Seems like we're heading down a road here where we might have that same situation where we're going to match up and compare the terms that do not have I in them and the terms that do, and maybe make a system of equations. So we're going to move everything away from our square root here, and we have the square root of a squared plus b squared is equal to, well, let's keep the terms without I together and the terms with I together with this sort of like, again, that real plus imaginary portion of our complex number. So we have 5 plus b, and we have minus ai minus I. Okay. Now, at this point, you may want to take this equation and square both sides, but we're going to be squaring a 4-term expression, which is going to probably become quite a mess. But if we write the right-hand side of this equation in this real plus imaginary form of a complex number, we have the square root of a squared plus b squared is equal to 5 plus b. Already had that. And I'm just going to put a parentheses around this to highlight that that's like the two terms with no i's in it. And we're going to factor out an I. I don't know why I just wrote t. Factor out an I. That's going to give us, and I'm going to write a plus sign here so I don't have to worry about these signs, because I do want it sort of like an a plus something I. Well, not a, because that's getting confusing because there's a here, but some real term plus some imaginary term of our complex number, negative a minus 1. Now, the modulus of a complex number is the distance that between the complex number in space on the complex plane and sort of that origin or the center of that coordinate system, which means that this is a distance. And distances have to be what? Real numbers. So if the distance between the center of the complex plane and the complex coordinate has to be a real value, then the coefficient of I, this has to be equal to 0. Otherwise, you're leaving the door open to this modulus being basically a complex or an imaginary number. So with that understanding, negative a minus 1 has to be equal to 0, which means that negative a is equal to 1, which means a is equal to negative 1. A has to be negative 1 for this coefficient of I to be 0, thus forcing this modulus of our complex number to be a real value. And now, using that fact, we have the square root, so therefore, we have the square root of negative 1 squared plus b squared is equal to, well, 5 plus b. And we are setting, we're making a equal to negative 1. We're forcing this imaginary term to be equal to 0, again, for that modulus to be a real number. Now we're going to square both sides, and we have, and negative 1 squared is 1, so we have 1 plus b squared, and I guess I probably should show it. Squaring both sides, we have 25 plus 10b plus b squared. Both sides of our equation have b squared, subtracting that from both sides. And we're now going to subtract 25 from both sides of our equation. And we have negative 24 equals 10b. Dividing both sides by 10, we have negative 12 fifths is equal to b. Now, before you celebrate, you are not asked to find the real values of a and b in this problem. You're asked to find the complex number z that satisfies this equation. So make sure you format your answer correctly, or that you actually answer the question. Z is equal to negative 1. This is so exciting. Minus 12 over 5. And that is the end of this example. I got just one more coming up right now. Na, 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 na. It's the last example. What conditions must the real and imaginary parts of a complex number z satisfy so that 2 minus 7i over z star thingy is purely imaginary? Well, I don't know what notation your book is using, but hopefully it's the same. This represents conjugate in the book that I'm teaching from. So basically, we want 2 minus 7i divided by the conjugate of z to be purely imaginary. So instead of z being a plus bi, we're looking at z as being a minus bi. Oh, so basically we just need to rationalize, if you will, this complex fraction, get the I out of the denominator, and then just figure out what needs to be going on with A or B or the combination of whatever to make sure that this is purely imaginary. So we're going to multiply the numerator and denominator by the conjugate. So we're going to have A plus BI multiplied to the numerator and the denominator. That's going to give us 2 times A and 2 times BI. And now we have negative 7ai and negative 7b, and then I times I is I squared, all over a squared minus b squared I squared. Okay, well don't forget, right, that I squared is equal to negative 1. So we've got minus 7bi squared is the same as plus 7b, so we're looking at 2a plus 7b. I'm putting these two terms together because they don't have a factor of I, plus bi minus 7ai all over, well, again, with this I squared being negative 1 times b squared is negative 1 times negative b squared is plus b squared, which a squared plus b squared is going to be a real value. We're going to take out this factor of I and create a coefficient for the imaginary term of our complex number. And we have 2a plus 7b plus b minus 7a, which is our coefficient of I. And I'm also going to actually separate this into two separate terms where we have this is over a squared plus b squared, and this is again a squared plus b squared, which is going to be a real value. Now we want our complex number to be purely imaginary, which means that we want the real term to be equal to 0. And the only way you make a fraction equal to 0 is if the numerator is equal to 0. So therefore, we have that 2a plus 7b has to be equal to 0, and we're looking for the real and imaginary parts of a complex number z. So we are looking for some kind of complex number z, and we're looking for the real and imaginary parts. So we have that 2, which a is the real part of this complex number, the 2 times the real portion, make sure I use the right symbol here, the real portion of z plus 7 times the imaginary portion of z, which is a plus bi, has to be equal to 0. And that is the end of our last example. I hope this helps. I'm Mr. True. Bam! Go do your homework.